In this video, we'll derive the consistent mass and stiffness matrix for the beam element, as well as the force vector, the vector of nodal forces. We'll proceed in exactly the same manner as we did for the bar element, and that is starting with writing out the kinetic energy for the beam. That can be written for a uniform beam as 1/2 times rho times the cross-sectional area times the integral from 0 to L. This is the mass, the integral from 0 to L of W dot, which is the velocity, squared, dx. The velocity is a function of both x and t, but for shorthand, I'm just going to omit it here. I remind you that W of x and t is assumed to be able to be written as some vector of shape functions, which we call phi transpose, times the nodal displacements q. So the shape functions are a function of x only, and the nodal displacements are a function of time only. Call this equation 1 and equation 2. Okay, substituting equation 2 into equation 1 gives us t equal to 1/2 times rho a times the integral from 0 to L times q dot transpose times phi transpose times q dot dx. The reminder that we take the dot, the time derivative, only on q because q is the only part that's time dependent. I can rewrite this as this equals, take the q transpose out because it's a function of time only. We can take it out of the integral. Q dot transpose times, let me change color for this, rho a times the integral from 0 to L of phi times phi transpose dx, change color back, times q dot. Okay. I remind you that the vector phi, you can see this from a previous video on the bar element, the vector phi transpose is just simply phi 1 of x, phi 2 of x. In the bar element, we only had 2 shape functions. Now we have 4. Phi 3 of x, phi 4 of x. And the reason we have 4 is because this beam element has 4 boundary conditions to satisfy. So continuing, we know we can write the kinetic energy in matrix form as 1/2 times, oh, I left out my half in the line above. Let me add that back. 1/2 times q dot transpose times the mass matrix, which I'll do in blue, times q dot. And from this, it's easy to see that the mass matrix M is simply equal to rho times A times the integral from 0 to L times the vector phi times phi transpose dx. We'll call this number 3. 1, 2, 3. This, by the way, is exactly the same as we came up with the bar element. The shape functions obviously are different, but the formula is the same. Okay. The strain energy of a beam, U, can be shown to be a uniform beam 1/2 EI times the integral from 0 to L of W, x, x dx. W, xx squared dx, excuse me. Okay. We'll call this number 4. By substituting the assumed W, equation 2, into equation 4, we can rewrite this as, this equals 1/2, I'm going to take the Q out, times, let's change color again, EI, times the integral from 0 to L of phi comma xx, the second derivative of phi with respect to x, times phi comma xx transpose dx, and that's times q. But we also know that the strain energy in matrix form can be rewritten as 1/2 times q, excuse me, this should be a q transpose, 1/2 times q transpose times the stiffness matrix K times, I want to do that in blue too, just to make the point, stiffness matrix K times Q. Okay. This implies that the stiffness matrix K can be written as EI times the integral from 0 to L of phi comma xx times phi comma xx transpose dx. Call that equation 5. Okay, and so we have the equations for both the mass matrix and the stiffness matrix. What's left to be found are the shape functions phi. Let's make some room here. Now, in the case of the beam, we have 4 boundary conditions, 4 different displacements, nodal displacements at the edges, 2 on each edge. So we can write the vector q, or q transpose of t, is equal to q1 of t, q2 t, q3 of t, and q4 of t. And because we've got 4 nodal displacements, we also need 4 shape functions, 1 for each. So the vector phi, or phi transpose of x, is equal to phi1 of x, phi2 of x, phi3 of x, and phi4 of x. So what remains is to find these shape functions, phi. We're assuming a displacement field w of x of t, as we said above in equation 2, is equal to something like a0 plus a1x plus a2x squared plus a3x cubed. Let's give these some numbers, 6, 7, and 8. So we have 4 different constants to solve. We've got 4 boundary conditions. We can solve for them by applying the boundary conditions. The first boundary condition says that w at 0, comma t, is equal to q1. w prime, I should say, w comma x, the derivative with respect to x at 0, comma t, is equal to q2. W at L, comma t, is equal to q3, and w comma x at L, comma t, is equal to q4. We'll call these equations 9. So if I substitute 9 into 8, what we find, and I'll save you the algebra, is that A0 is equal to Q1 of t. A1 is equal to, A1 is equal to Q2 of t. A2 is equal to 1 divided by L squared times minus 3 Q1 of t minus 2 Q2 of t times L plus 3 Q3 of t minus Q4 of t times L. And finally, A3 is equal to 1 over L cubed. That's squared, 1 over L cubed, times 2Q1 of t plus Q2 of t times L minus 2Q3 of t plus Q4 of t times L. Let's turn the page. We can now find our shape functions phi by substituting the results for the a's back into equation 8. Let me write that. So substituting the ai's into 8 and collect the coefficients of Q. And what we find is that phi1 of x is equal to 1 minus 3 times x over L squared plus 2 times x over L cubed. Phi2 is equal to x minus 2L times x over L squared plus L times x over L cubed. Phi3 is equal to 3 times x over L squared plus, minus 2 times x divided by L cubed. And then finally, phi4 of x is minus L times x divided by L squared plus L times x divided by L cubed. Let's give these some numbers. 8, 9. We'll call this one 10. Oops. 10 are the A's. And then these will be 11. So that all that remains now is to substitute equation 11 into equations 3 and equation 5 in order to determine the mass and stiffness matrices. When you do that, I'll save you the algebra, you find that, well, let me write this, 11, it's 11 into 3. And what that does is it gives a mass matrix, M is equal to rho A L divided by 420 times 156, 22L, 54 minus 13L, 22L, 4L squared, 13L, and minus 3L squared. Next column is 54, 13L, 156, and minus 22L. and then minus 13L minus 3L squared minus 22L, and finally 4L squared. We'll call that 12. That is the mass matrix, the consistent mass matrix for the beam element. The stiffness matrix, K, this is found by substituting 11 into 5. Remember that we first need to take the second derivative of x with respect to the shape functions before doing the substitution. And that gives us K is equal to EI divided by L cubed times 12, 6L, minus 12, 6L, 6L, 4L squared, minus 6L, and 2L squared, minus 12, minus 6L, 12, and minus 6L again, and then 6L, 2L squared, minus 6L, and finally 4L squared. We'll call that 13. That is the stiffness matrix. And then finally, all we need to find out is what is the consistent force vector. That comes from the principle of virtual work. And from the principle of virtual work, we can say that del W is equal to the integral from 0 to L of f of x of t, this is the distributed load, times del W of x comma t dx. All right, through substitution, we know what our assumed displacement field is. We can rewrite this as del Q transpose times, I'm going to change color again for this, the integral from 0 to L of phi of x times f of x t dx. And we know that this is equal to del Q transpose times the vector of modal forces f of t. Follows from this that the vector f of t is the integral from 0 to L of phi of x f of x t dx. And I'll remind you, since I didn't put it in this video, but F is some sort of distributed load. And you can go back to the beam problem, I'll put a link to it here, but this is F of xt. It's an applied distributed load per unit length across the beam. And before closing this video, I'd like to go through the determining of the shape functions again, this time using matrix algebra to show how it can be made a lot easier. So again, we've got our beam. The first idea was we assumed that it had a displacement field W of x and t was equal to some vector of shape functions, phi transpose, times q. And I forget where we were with the numbering. 13, this would have been 14. And this will be 15. Okay. Where remind you that phi transpose of x is equal to phi 1 of x, phi 2 of x, phi 3 of x, and phi 4 of x. Whoops, put the bracket in the wrong place. And that q of t, q transpose of t, is equal to q1 of t, q2 of t, q3 of t, and q4 of t. Okay. The second step was to assume a displacement field that would satisfy all the boundary conditions. Assume displacement field. And this was W of x and t was equal to a0 plus a1x plus a2x squared plus a3 x cubed. Okay. In doing so, we could write W in matrix form as some vector which we'll call x transpose, vector of x times a. Where in this case x transpose of x is simply equal to 1 x, x squared, and x cubed. And the vector that we've called a of t, transpose, is equal to a0, a1, a2, and a3. All right, so that's 15, we'll call this 16. Step 3. We applied the boundary conditions. And as an example, we said that W at L comma T, which is equal to Q3, is equal to A0 plus A1L plus A2L squared plus A3L cubed. So I'm going to suggest that we could write our Q's equal to some matrix of coefficients, which we'll call B, it's a square matrix, times our A vector. Right, and as an example, Q3 is 1 times A0, L times A1, L squared times A2, and L cubed times A3. So by applying the boundary conditions, we can rewrite it in this form, which I'll call equation 17. Now, instead of going through all the tedious algebra of now rewriting the A's in terms of Q's, which is what we need to do, we'll do that in step 4. Solve for A's. In matrix form, this is very easy. We just write that A of t is just B inverse times Q of t, vector Q of t. Call that equation 18. So instead of having to rewrite this tedious algebra, if we just stack the coefficients in a matrix we call B, we can use various programs to solve B inverse. And I'll put a reference here for Wolfram Alpha. .com. It's a website, a free website that will allow you to do this. It will do it for you. And by this I mean it will allow you to invert symbolic matrices. It can do a whole lot of other stuff too, like perform your integrations, for example. And then finally, we need to find phi of x. And the way we find phi of x is if we take equation 18 and we substitute it into equation 16. So let me write that here. If we substitute 18 into 16, we find that w, let me just rewrite this. I want to say find this. Find phi of x. All right, so this gives us w of x of t is equal to, you write it out in first, x of x transpose times a of t. This is just from equation 16. Now I want to substitute this in here for a. So that equals x transpose of x times b inverse times q of t. However, we know from equation 15 that this is equal to phi of x, phi transpose of x, times q. Should put q of t up here at the top, q of t. All right. So therefore, we can find phi of x, phi transpose of x, as x transpose of x times the inverse of the B matrix. All right, and that is it. That I'll call equation 19. If I can get this to right, equation 19. Right, so just to recap, we need to find this matrix called B, and we find B by applying the boundary conditions. We get the inverse of B using a mathematical package, and then we can get our shape functions just by multiplying this x vector, or the transpose of it, by the inverse of the B matrix, and that gives us our shape functions. And you'll find that makes it a lot easier to find if you wanted a more complicated beam, like maybe you wanted a beam with an internal node or a beam with two internal nodes, where you'd have more complicated shape functions and the algebra becomes very, very tedious indeed. However, if you handle it in matrix form, you'll find it very much easier. Anyway, that brings us to the end of this video. I hope you found something useful. If you have, please go ahead and give us a thumbs up, or better still, why don't you subscribe to the channel? Thank you very much for watching, and we'll catch up with you in the next video.